Fantastic.
The floor is yours.
Great. I'm hoping that the microphone is working now, and I think we have slides.
Yep.
So, as mentioned, my name is Jelena Notaros. I'm an assistant professor in the Department of Electrical Engineering and Computer Science here at MIT. I want to thank ILP for the invitation to talk to you today. It's incredibly exciting to be in person, to actually see you guys in 3D as opposed to little boxes. This is, I think, the first presentation in person other than teaching. In teaching, there's just a lot more chalk involved, so this is a little cleaner. But yeah, I'm excited to introduce you to my group's work in silicon photonics. I'll start with an introduction to silicon photonics and some of the other efforts I've been a part of in the past, just to give you a flavor for the immense impact that silicon photonics can have on a number of application areas. And then we'll focus in on integrated optical phased arrays. I'll start with beam steering phased arrays and their primary motivator, which has been lidar for autonomous vehicles. So chips that actually steer light around and can get that lidar return. Also for transceivers for optical data communications. And then we'll take a look at taking these phased arrays and bringing them to the visible light regime and integrating 1,000 of them on a chip that's completely transparent, that sits in front of your eye, and that projects holograms for augmented reality. So let's start first with silicon photonics. So the general idea behind silicon photonics is that we're taking standard CMOS fabrication processes and tools, and we're repurposing it to create optics on chip. So on the bottom here, you can see a cross-sectional view of a silicon photonics platform that we've developed in the past. This is based on then IBM 12SOI, now Global Foundries. On the left, you can see here the bulk CMOS transistor. You have the silicon layers, some doped silicon, and then some metal coming down into contact to modulate that electronic signal. And what we can do is we can take all these layers and we can repurpose it to create our photonic devices. So in the center here, we have a rectangular silicon-based dielectric waveguide. It's confining light on the chip and guiding light down the chip. We can then dope certain regions of that silicon and place metal down into contact, and that enables us to modulate the light on the chip, to have control of the light and what's happening. And then we can create interesting patterns in the silicon for optical antennas or grating couplers that emit the light up and out of the chip and enable us to interact with the surroundings of the chip. So by developing these silicon photonic platforms, we have a way to take optical systems that were once complex and bulky and expensive. Maybe they took up an entire optical table in one of the labs here at MIT, and we can take that system and we can integrate it onto a completely flat millimeter scale chip. Also, by utilizing these standard CMOS fabrication processes that are fabricated on the wafer scale, you can see one of our 12-inch wafers over here. By using these fabrication processes, we have a way to create very low-cost and high-volume optical systems. And also, by taking advantage of these mature CMOS fabrication tools, we can create optical devices with very high fidelity. So that enables us to create systems on very large scale, so on the order of 10,000, maybe even up to 1 million devices in a single optical system. And then finally, by integrating these components onto chip, we can enable new functionalities that were never before possible in bulk optics or fiber optics. So before I get into integrated optical phased arrays, let me introduce you to some of the other efforts I've been a part of, again, just to give you a flavor for the vast array of applications that this technology can address. So silicon photonics has historically been driven by the optical interconnect industry. And the idea here is, can we replace the electrical or copper interconnects, for example, in your computer, between the memory and the multiple cores in your computer, or the electrical interconnects in a large-scale system like a data center, the electrical interconnects within the rack, with some optical counterparts, so an optical interconnect. And to address this need, we developed the first microprocessors that actually run on these optical links. You can see a diagram of one of them here. And one of the main components in there is this grating coupler that couples light from an optical fiber onto your photonic waveguide. As part of this effort, we demonstrated the highest efficiency grating couplers. I believe this is still the record to date. We can also develop nonlinear photonic platforms on chips. So you can see here an example. Here we're integrating rare earth doped aluminum oxide gain material in with the silicon photonics that allows us to create interesting lasers like mode lock lasers or tunable lasers to generate optical frequency combs or very precise frequency synthesis. This might be interesting for some people in the room that are thinking about creating precise chemical gas sensors. You need these kinds of frequency combs and very precise frequencies as references. And then also, silicon photonics is poised to have a large impact on the emerging field of quantum communications. Here you can see an example of a silicon photonics-based transceiver that we demonstrated that does quantum secure, sends information in a quantum secure way using a novel protocol that we developed. And more recently, we've been thinking about how do you create these photonic devices in a cryocompatible way. So again, I don't have time to go through all of these different efforts in detail, but I'd be happy to talk to you about them afterwards. So for today's talk, I'll focus in on what we call integrated optical phased arrays. So let's first take a look at kind of standard phased arrays, beam steering phased arrays, and their primary motivator, which has been lidar sensors. And I think this kind of nicely even ties in, lidar sensors we normally think about for autonomous vehicles, but even ties into the previous talk, how the previous speaker was mentioning that they need lidar to even navigate these tools, the tapeworm tool into the body. Again, tapeworm, I think that's sticking. So, but here we'll primarily kind of focus in on autonomous vehicles. So if you take a look at a current autonomous vehicle, you'll notice this large instrument sitting on top of the car. This is the car's lidar module. And what this lidar module does is it sends out a pulse of light, and then that light pulse reflects off the surroundings of the object, of this car, and then based on the delay of the light pulse, the lidar sensor is able to calculate the distance to the reflected object. This entire module then spins around mechanically to create a three-dimensional map of the car's surroundings. However, this is a nice solution, but there are quite a few limitations. So first, this is a mechanical system. So you can imagine some mechanical degradation or slippage over time, especially in adverse weather conditions like we have here in Boston. Second, since this is a mechanical system, it's historically been incredibly expensive. So this isn't an economically feasible or scalable solution. And third, and I think most importantly, because it's using this pulsed modality, which we call time-of-flight lidar, it's limited to near or mid-range sensing. It can't quite reach the few hundred-meter range that's required for autonomous vehicles. We need to bring in some kind of coherent solution for these sensors. So it's clear that there's a need for a new type of lidar sensor, and specifically one that can steer that optical beam in a non-mechanical way. And that's where these integrated optical phased arrays come in. So the optical phased array borrows heavily from its radio frequency counterparts. Maybe some time ago you learned about these phased arrays in your EM class. I actually just taught this topic today in my graduate EM lecture. So I remember now the math very clearly. But the general idea is that we individually control the amplitude and phase of the light or the RF signal that's emitted out of each of these antennas. And by individually controlling those phases, we can dynamically control the light that's emitted out of the array itself. And when we leverage the deeply scaling power that I talked about of silicon photonics, we can now take these optical phased array technologies and we can demonstrate optical phased arrays with greater than 10,000 antennas on a single millimeter scale chip. So this allows us to have a very low cost, compact, and high-speed method to do this kind of non-mechanical optical beam steering for applications such as lidar sensors for autonomous vehicles or perhaps transceivers for free space optical data communications. So let me talk you through what does one of these optical phased arrays look like. So this is a cascaded architecture that we developed in the past. So here we have our input to the chip. There's some kind of coupler there. And we have our silicon waveguide that kind of snakes around here. We call that the bus. And then we place these evanescent tap couplers, so another sets of waveguides, kind of in close contact with that bus waveguide. And that allows us to couple light from the bus to these antennas here. When the light enters the antenna, it sees these perturbations in the antenna sidewalls, and the perturbations are placed periodically, so the light actually kind of scatters up and out of this antenna. Now, because we have multiple antennas here, that light, if it's coherent, is going to form a beam in the far field of the array. We can then place thermo-optic phase shifters that I'm showing here in yellow, so we can dope that silicon, and we can apply a voltage across those thermo-optic phase shifters, and by applying a voltage, we're going to heat up the silicon, which changes its effective index, which effectively slows down the light or applies some phase shift to the light as it's traveling through this bus waveguide. So in this way, by applying the voltage, we can apply a cascaded phase shift or a phase gradient along this bus, or in other words, we can apply a phase gradient to those antennas. And if you remember that animation that I showed you earlier, this phase gradient is actually what determines the angle that you're emitting out at. So if you have a larger phase gradient, your angle is going to be larger there. So you can have electronic control over the beam steering or the angle that you're emitting at in the array dimension. Great, so we have tuning of the beam in one dimension. How do we tune the other one? So to do that, we change the wavelength of the light at our input, and this change in wavelength manifests itself in these grading-based antennas. You change the wavelength, the effective period of the grading changes, which changes the angle that the light is emitted out at. So overall, we have a two-dimensional phase beam steer. We have voltage-controlled beam steering in the array dimension, and wavelength-controlled beam steering in the antenna dimension. So I would love to go through all the details of the different systems that we developed here and kind of the intricacies of that, but unfortunately I don't have time. So I'll just give you a highlight of some recent results that we've shown. So these optical phased arrays, they're fabricated in a CMOS foundry in Albany in 300 millimeter wafer, so 12 inch. In a platform that we developed in collaboration with SUNY Poly in Albany. And if you're familiar with silicon photonics, this platform that we developed is actually the basis for the current offering by AIM Photonics. We then used this platform and we demonstrated that cascaded phased array integrated with an on-chip laser. This is an erbium-doped DFB laser. And showed beam steering by changing the voltage across that phased array using this electronic probe, but with this integrated laser. So you no longer have that off-chip laser. Of course, the next step is how do you tune the wavelength that you're putting in to get that beam steering in the antenna dimension that I talked about. So to address that need, we developed a tunable laser based, again, on that erbium-doped aluminum oxide gain material. Now, of course, I mentioned that we applied a voltage using this kind of external probe, and in the lab, that's nice because we have some Keithleys and we apply voltage and everything's great. But of course, in a commercial product, you need to be able to scale this up to many antennas to be able to get a very tightly focused beam. So you need to have a way to integrate your electronics also on the chip. So to do that, we developed a 3D integrated a 3D heterogeneously integrated electronic photonic platform. So we have our 300 millimeter photonics wafer, and then we also fabricate a compatible 300 millimeter CMOS electronics wafer. We bond the two wafers together. We then have through oxide vias, and that allows us to have electronic control of our photonics using CMOS electronics on the same chip. And using that platform, we demonstrated one of those cascaded phased arrays actually driven with some CMOS electronics directly underneath. And with that same platform, we then took the next step and demonstrated a lidar result where we have a transmitter array, a receiver array. The light comes out of the transmitter, bounces off the target, comes back to our receiver. We then have some photonic components that process that return, and then CMOS to actually take that optical signal and directly convert it to a lidar output. I don't have time to kind of go into all the details, but I also mentioned that this work is now spun out to a startup, Analog Photonics, that is really taking this and making a commercial product out of it, which is incredibly exciting to see. So next, so in this previous section, I talked about these optical phased arrays for lidar. These were operating at infrared wavelengths, so 1550 nanometer, to be in kind of the eye-safe regime. And they were operating in kind of a standard phased array configuration that you probably learned about in your EM course, where you have these antennas, and they're forming a beam in the far field. However, now we're interested in what could we do if we take this phased array and we bring it to the visible light regime, and then we don't have just a single array that's forming a beam. We integrate 1,000 of these arrays all together on a single chip, and then we control both the phase and amplitude and actually project holograms for the user to see if you place this on a transparent chip for augmented reality. So let me give you a brief introduction to that. So if you take a look at a current augmented reality display, maybe some of you actually own a pair of these AR head-mounted displays. It's definitely a large and heavy item. It definitely wouldn't be considered discrete. I would know if you were wearing one. Also, if you put one of these guys on, if you've ever tried it out, the information is actually limited to a small area of your vision. The display has a limited field of view. Also, if you were to take these glasses outside on a really bright, sunny day, you'd notice that the information is kind of washed out. That's because the display has a low luminance. And then finally, that information is projected onto a single focal plane. So for example, if I was projecting information about John here, my eye would constantly have to focus from the display plane back to John, back to the display plane, back to John, back to the display plane. And the focusing of your eye is controlled by the muscle in your eye, right? So if your eye constantly has to do this refocusing, it causes eye strain. And for many people, they develop headaches because of this. This is a very well-known effect. It's called the vergence accommodation conflict, and it limits long-term usage of these displays. Of course, if you're using this for personal use, or if you're a doctor, maybe you're doing some surgery, you want to display information, you want these glasses to be very comfortable. So to address all of these limitations, we developed an integrated photonics solution for our augmented reality display. It consists of a single, completely transparent chip that sits directly in front of your eye. Perhaps it's integrated in a pair of glasses like some of you are wearing here, where I wouldn't even be able to tell that you're wearing it. Because it's sitting directly in front of your eye, we can then encode the information that's projecting out using both amplitude and phase encoding and project full three-dimensional holograms for the user to see. So this enables a fully holographic and highly discrete solution for the next generation of augmented reality technology. And the general idea behind this Viper display is that we take that optical phased array technology and we bring it to the visible light regime, and we create this optical phased array-based pixel based in silicon nitride that's tuned using an integrated liquor crystal modulator. We then put 1,000 of these in a two-dimensional grid. And then in order to get that holographic information to project out, we not only control the phase gradient that I talked about kind of in the first part of the talk. So we not only control that phase gradient using this liquor crystal, but we also control the amplitude and the absolute phase relative to each of these pixels. And that allows us to have very exquisite control of both amplitude and phase to get a holographic image to come out. Again, I don't have time to go into a lot of detail on exactly how this works, but I'm super happy to answer questions at the end if people are interested to go more in depth into it. But I'll give you a little bit of a highlight reel of recent results. So of course, our first challenge was, how do you actually create a computer chip that you can put in front of your eye? If you were to take a current computer chip out of your laptop and put it there, it's based on silicon. Silicon absorbs at visible wavelengths, so you wouldn't be able to see out of it. So in order to address this, we developed first a visible photonics platform based, again, on 300 millimeter wafers. and this is based in silicon nitride waveguides as opposed to silicon. And then we take that, platform that we developed and we bond it to glass. And you can see here the final wafer held up by one of the students. And this wafer, you can kind of see the outline here. It's actually really hard to tell because it is quite transparent. And all the photonic waveguides are included there. And then we could dice it up to get our individual chiplets. Using this platform, we demonstrated kind of a first proof of concept of a passive version of this holographic display. And this guy, if you were to put it up to your eye, this is projecting a virtual image of a three-dimensional holographic cube. So the key word there is a virtual image. So if you were looking through this guy, you would see this cube floating out in space about a meter away, but everyone around you wouldn't be able to see it. Again, if you're interested, I can give more details about this. Of course, this is super exciting for us, especially when we looked into it. I don't know if we were supposed to, but we did. This is just one cube. We're interested, can we take this a step further? Can we create video holograms? Can we create multiple images? And the real challenge here was that visible light is incredibly hard to modulate on chip. Silicon nitride has a very low thermal optic coefficient, effectively no electro-optic properties. So any kind of modulator for these visible waveguides would be incredibly long. So instead, we integrated liquid crystal material, that's a birefringent material, in with our silicon nitride waveguides, very close. And by integrating this close approximation between the mode in the silicon nitride waveguide and the liquid crystal, we can get modulators that are kind of orders of magnitude smaller than what you would normally have in a visible modulator. And we demonstrated both phase modulators and amplitude modulators using this technology. We then also used this liquid crystal integration to demonstrate the first actively tuned visible light optical phased arrays. And you can see here a photograph of the chip sitting there, and it's projecting light out. And you can see some beams that are formed there. Again, this is just that one phased array, so it's forming a beam in the far field. And then if you apply a voltage using those probes, you can get that beam to steer around. And then we took all of these different components, the phase modulator, amplitude modulator, and then that phase gradient tuning, brought it all together and started working towards a proof of concept demonstration of that full active Viper display. So of course, this current Viper technology, we envision it for head-mounted displays. It has very efficient components for daytime operation based on a single transparent chip, so it's a very compact and discrete solution. And it projects holograms, so it resolves the divergence accommodation conflict and enables long-term use. But I think what's exciting is thinking about the even broader impact of this, perhaps on the display technology as a whole. Could you integrate many of these Viper chips together to potentially create a solution for a transparent holographic TV? I think there's super exciting and interesting things to think about for the future. So overall, I introduced you to silicon photonics and some of the efforts that I've been a part of in the past, and then showed you some of our work in beam steering optical phased arrays for lidar and visible light optical phased arrays and systems for augmented reality. But I hope that this, in general, gives you a feel for what my group and my team here at MIT is working on. We're developing novel silicon photonic platforms in collaboration with standard CMOS fabrication foundries. We then use these platforms to demonstrate new kinds of photonic devices using first principle electromagnetics and device physics. And then we're integrating these devices in very large-scale optical systems on the order of thousands or millions of components to enable novel solutions for many high-impact application areas. So today we talked about lidar and augmented reality displays. We also have efforts where we're thinking about using these chips as transceivers for free space optical data communications in collaboration with Lincoln Lab. We have some fun work where we're trying to use this chip to actually make a completely compact 3D printer that operates at visible wavelengths, so it's also biocompatible. we're thinking about how can we use chips to interface with the body. Could you have a chip that's sitting outside of the body and using this holographic image modality to enable more efficient sensing or actuation of material? So we have some exciting results that will be coming out pretty soon on that. And then we also have efforts in quantum engineering, again, in collaboration with Lincoln Labs and other teams around MIT. We're using these photonic chips to address trapped ions for quantum computation and sensing, and also ultra-cold atom arrays. So with that, I'll give a big acknowledgement to my team at MIT and all of our collaborators, both in the past and current. At MIT, we're really focusing on photonic device and system development, laying out these systems, thinking about what are the applications, and actually doing the experiments. These devices were fabricated in collaboration with SUNY Poly in their CMOS line there. And then the CMOS electronics work was done in collaboration with Professor Vladimir Stoyanovich at Berkeley. Shout out also to funding agencies, mostly through DARPA, EFI, DODOS, POEM, and VIPER programs, in addition to some support from the NSF. So with that, super happy to take any questions. You can also see my email down below if you want to shoot me an email afterwards.
Great, terrific. I'd love to hear what your questions are, and we've got one right over here.
Okay, you can't drop a phrase in like ultra-cold atom arrays without explaining what you're going to try and do with them. It's too cold to just mention. Ultra-cold atom arrays you mentioned? What's the application space?
Yeah, so the idea here is if you've ever been in kind of a atom array lab, you usually have this gas that's sitting in some chamber, and then you have a bunch of optics all around it. Of course, these optics usually cover an entire optical table and are very complex. You have different wavelengths coming in, different beam sizes, different functionalities. So what we're looking into is, could you actually integrate all of that functionality, including different wavelengths, different beam properties, into a single chip? And a big application, of course, the ultimate goal for all of these different types of qubits is quantum computation, in addition to sensing.
Terrific. Other questions?
Just wondering about typical power utilization and thermal.
Yes. So thermal modulation is actually incredibly power hungry. So that's a great question, because I specifically mentioned thermo-optic modulation, but normally with thermo-optic modulation, to get some reasonable beam steering, you would need something on the order of a watt of power. So instead, what I didn't show results here, but instead what we're kind of moving towards is electro-optic modulation, where you have doped silicon, you're still applying voltages, but you're actually getting kind of carrier effects there. And there you can get microwatt powers per a phase shifter, so something on the order of a milliwatt to power this entire thing. That's, I think, these kinds of considerations, I think, are incredibly important when you actually move towards a commercial product. Like I mentioned, there's fantastic work coming out of the startup that spun out of this analog photonics. But another thing that you could think about, thermal optic modulation is normally quite slow, so on the order of kind of megahertz type of speeds. Electro-optic, you can get much faster, tens of gigahertz. That's not necessarily as much of an advantage for these lidar systems, because if you think about it, you have the actual power to do the phase shifting, but then you have the power to actually drive those electronics. And if you try and move this guy too fast, you don't get that much win in terms of like the actual autonomous vehicle application, but you end up using a lot more power for this entire system. So you want to drive this thing closer to like maybe 100 megahertz.
We have one last question.
Yes, Janos Rohai from Jazz Site. Can the same approach be applied for imaging when you can create extremely thin imaging sensors and optics very close to the target? Thank you.
Yeah. This is something we're super interested in looking into, and we have some new efforts thinking about this. The biggest challenge, I would say, is how do you make your detector, your detection efficiency large enough so that depending on what you're imaging, if it's something in the body, there's going to be so much scattering, and body is a terrible reflector. So you need to really innovate on the detection side. But yeah, you can definitely use these kinds of sensors to do imaging. It would just be a question of changing up the architecture based on what actual material system or what application you're looking into.
Terrific. One more thanks for Professor Notaros.
Thank you so much.